Right. So welcome everyone to Purdue ECS chapter webinar series. And this semester we have a theme of solid-state batteries. If you don't know me, I'm Prof. Mukherjee from Purdue Mechanical Engineering, and I serve as the faculty advisor to this chapter. On the audience, I probably see Professor Rebecca Cheese, for also a faculty co-advisor on this chapter. If I'm missing others, sorry, but I'll let Devanjali do the formal introduction of our speaker, but I am very pleased to have Professor Matt McDowell from Georgia Tech joining us today and finding time to speak here. And Matt and I, of course, know each other quite well. Also, we have we're good friends and also collaborators. With that little introduction, thank you, Matt, for joining us today and finding time to speak here. And hand it over to Devanjali for the formal introduction. Thank you.
Thank you, Professor Mukherjee. Let me share my screen. Okay. Is my screen visible to everyone?
Yes.
Okay. Hello, everyone. I'm Devanjali Chatterjee, a PhD student at the Energy and Transport Sciences Lab at Purdue and president of the ECS Purdue student chapter. Welcome back to our fall webinar series on solid-state batteries and electrochemistry. So the ECS Purdue chapter comprises of over 20 student members led by the chapter officers under the guidance of the chapter advisory board. Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue is our lead faculty advisor. We have Dr. Judy Jeevarajan, Vice President of Research at Underwriters Laboratories as our distinguished industry advisor. Professor Rebecca Chase from the School of Mechanical Engineering and Professor Julia Laskin from the Department of Chemistry at Purdue are our co-faculty advisors. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering, which was exceptionally well received and appreciated in the scientific community. Inspired by its success, this semester, we have launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry. Today, our speaker is Professor Matt McDowell from Georgia Tech, an associate professor with appointments in the Woodruff School of Mechanical Engineering and the School of Material Science and Engineering. He received his PhD from Stanford University in 2013 and was a postdoc at Caltech from 2013 until 2015. Professor McDowell has received numerous awards, including the Presidential Early Career Award for Scientists and Engineers, Sloan Fellowship, NSF Career Award, AFOSR Young Investigator Award, and the NASA Early Career Faculty Award. Today, he will be speaking on understanding the evolution of materials and interfaces in solid-state batteries. Professor McDowell, we look forward to your talk.
Great, thank you very much. Let me share my screen here. Does that look good?
Yes, it's perfect.
Excellent. All right. Well, thanks very much for the introduction. This is really quite an honor. I appreciate the invitation from the students. I guess it means that some people are reading my group's papers. That's great. And you know, I'm very familiar with the seminars that the Purdue ECS chapter has put on, you know, last week, but also last semester and last year with the Women in Electrochemistry seminar series. And you guys have done a great job. So thank you for that. So I'm a professor at Georgia Tech, associate professor at Georgia Tech, as Devanjali mentioned, and I will be talking about my group's work today on understanding the evolution of materials and interfaces in solid-state batteries. So I plan to tell you about a number of different areas that we're working on, including some new stuff that I haven't talked about before. So just as a quick overview of my group, most of my group is working on battery technologies and battery materials and systems. We also have another project focused on layered materials and transformation processes. But the overall scientific theme of my group is a lot of the things we do are focused on using experiments to understand transformation mechanisms in materials and devices. So we're working in a number of different energy storage areas. A pretty large portion of my students, about half of them, are working on solid state batteries. And that's what I'll talk about today. So many of you are probably familiar with this slide here, but I just want to provide a baseline level introduction. So we're very excited about solid state batteries because of their potential to enable higher energy density as well as improved safety for energy storage systems. So this is what a conventional lithium-ion battery looks like in schematic. And it has a graphite anode, a metal oxide cathode, and there's liquid electrolytes soaked throughout the structure. Transitioning to a solid state battery looks something like this, where we replace the liquid with a solid material that's shown here, the separator in the middle, that still conducts ions. And this improves safety because it's the liquid electrolyte in conventional lithium-ion batteries that can light on fire during thermal runaway. Another factor related to solid state batteries is you could potentially use different electrode materials, including lithium metal. And this allows you to boost your capacity and your energy density of your battery, something like around 50% in terms of specific energy, higher specific energy. So you can pack more energy into a smaller space and smaller weight. And this is exciting, of course, as probably many of you are aware, because we need these sorts of higher energy, safer batteries for new applications like electric airplanes or hybrid electric airplanes, as well as for electric vehicles that can travel further on a charge. So that's why we're excited about this. So why don't we have, commercialized solid state batteries already? Well, there are a lot of fundamental materials level challenges that are really quite interesting, scientifically intriguing, but unfortunately have prevented commercialization so far. And so I list some of these here. There's issues at interfaces with instabilities and interphase growth. There's contact loss of interfaces. There's filamentary growth of lithium metal to short circuit solid state batteries. Chemomechanics and the relationships between chemical changes and mechanical stress are very important in solid state batteries that can cause problems. And then also stack pressure, which I'll talk more about in this talk, plays a big role. So all of these things together are distinct mechanisms, and understanding how they interact with each other, understanding how they can cause degradation in solid state batteries is really important. So over here on the right, let me just show you kind of a schematic explanation of some of these issues. So on the top here, we have a lithium metal electrode in contact with a liquid electrolyte. And this is like in a conventional battery system with a liquid. If we charge and discharge this battery, the lithium metal electrode will change its morphology. And that's shown here. You can kind of see that we've changed the shape of this thing. And we've also grown an interphase, this purple region, which is a formation of a surface film. And the nice thing about a liquid electrolyte is even though we've changed the shape and the chemistry of this interface, the liquid still contacts the lithium metal. And this illustrates the properties of liquid. There's no shear stress that could be supported, and it's flowable into electrode porosity. So if we look now at the solid, it's a little bit different. We have a nice clean interface to start with between lithium metal and the solid electrolyte. But after we cycle, lithium metal has changed. It's changed its shape. There's now some areas where there's a void and there's loss of contact. And lithium metal can also grow through and fracture the solid electrolyte to cause short circuits. So this just kind of illustrates when you have a solid-solid interface, it's fundamentally different than a solid-liquid interface. And there are different sorts of challenges associated with it. And so historically, and even in recent times, visualizing and understanding these various processes has been difficult. So that's one of the things that my lab focuses on. So before I get into some of our results on understanding transformation mechanisms and degradation behavior, I want to provide some very new data actually from my group that illustrates the electrochemical degradation process that is seen in solid state batteries. So this is the sort of information you get from normal electrochemical testing. So in this configuration, we have lithium metal electrodes on two sides of a solid electrolyte material. This is the argyrodite LPS material with the chemical formula shown here. It has a high ionic conductivity. What we're probing in this experiment below is we're probing the short circuiting behavior when we have lithium metal that instead of growing in a planar fashion, grows through our solid electrolyte. And this test below is a test that's widely performed in literature. It's called a critical current density test. The way you do this is you take a cell like this, and then you apply currents in alternating directions, and the currents keep increasing and increasing until eventually your voltage falls, and that's when you have a short circuit that forms. So this is a degradation pathway, and it's actually the formation of these short circuits is a limiting factor in many solid state chemistries. So this is what people have seen in the literature, just for reference for those that are working in this area, we measure an average critical current density of 2.5 milliamps per centimeter squared. And so this is not new, but I'm showing you an electrochemical measurement of this degradation behavior. What's interesting, we've carried out a study recently, it's submitted for publication. This sort of short circuiting, is tested usually with these CCD tests. But what we've also found, which is kind of known in literature, but not really well quantified, is that if you just apply a current in one direction, basically move lithium from one side to the other without alternating back and forth, even at very low current densities, you eventually still get a short circuit. So what this means is usually it's thought that these short circuits only happen at high current densities. But in fact, you can apply a low current density, 0.6 milliamps per centimeter squared, for a long period of time or a longer period of time, and you eventually get a short circuit. And so this sort of degradation mechanisms where lithium is growing in these filamentary ways to short circuit a battery is prevalent across all sorts of different current densities. And so it's a big problem. And so again, I'm just emphasizing the electrochemical measurement of these sorts of degradation behavior. On this is a little bit more on this topic. So in this paper that we've submitted, we've quantified basically the amount of lithium that you have to pass before short circuiting in one direction as a function of current density. And if you understand this, you can actually tailor solid state cells to make them last a long time, actually, by keeping it below this, what we're calling threshold capacity. So hopefully this will come out soon, and you can check this out yourself if you're interested in optimized performance of solid state battery systems. But I think the big picture here is, we can do all sorts of different electrochemical measurements like this, and it's very helpful for understanding the limitations and behavior of these batteries. But for some of you in the audience, probably who aren't working on electrochemical measurements of solid state batteries, you look at this and you're like, well, what is actually happening here? And actually, even for people in this field, it's important to do more detailed experiments to probe how these sorts of electrochemical signatures are related to underlying materials mechanisms. So that's what I'll spend most of my time talking about here today. And so it turns out that you need to use multiple different types of experimental techniques to do this. Single technique will tell you some information, but usually you need to have multiple types of techniques. And so I'll tell you about different techniques we've used to probe the materials transformations and underlying dynamics in electrochemical systems. I'll first start with one of our recent studies using Operando X-ray tomography to probe contact loss at lithium interfaces. This is a pretty interesting study, I think, where we can map contact loss across large-scale solid-state interfaces. I'll then talk a little bit about interfacial stability and chemical changes in interfaces and how that influences degradation. And then I'll end the talk on our recent work focused on alloy anodes in solid-state batteries and using stack pressure as a diagnostic tool to understand structural changes in alloy anodes. So 3 different stories. I won't keep you forever, obviously. I'll try to finish on time. I will finish on time, I'll promise you. So don't worry too much about that. All right, so I'll start here with the first segment on understanding using synchrotron X-ray tomography to understand interfacial contact loss at solid interfaces. So I'll start here by showing some other literature data from a few years ago now. These are 2 very nice papers in which they use electrochemical methods examining the lithium interface with various solid electrolyte materials, actually. So here we have lithium metal in contact with this same argyrodite solid electrolyte. I believe this paper over here uses a different solid electrolyte. But what both of these studies showed is that there's some fundamental, from an electrochemical point of view, there's some evidence for fundamental contact limitations. And you can visualize this down here with this schematic. If you have lithium metal in contact with a solid electrolyte and you oxidize lithium metal, what you're doing is you're converting these atoms to ions and they travel through to the right through the solid electrolyte. But when you do that, you're removing lithium atoms from the lithium metal electrode. And so something has to come, another lithium metal atom has to come and take the place of that atom because you formed a vacancy. If you don't have replenishment of the lithium at the interface, then you'll eventually form voids at the interface, which is basically a contact loss mechanism, which can lead to very bad things, which I'll show you. And the basic theory here is that as you're stripping lithium from the interface, the rate of the flux due to self-diffusion of lithium from the underlying lithium metal, as well as the mechanical deformation of lithium. Both of these have to be, if they're less than the rate at which you're stripping lithium, then you're going to form voids. Nothing you can do about it. So it's a fairly simple idea. But we wanted to investigate this in more detail to understand how prevalent this void formation was, and to see if we could image it. So to do this, we took some custom cells to the Advanced Photon Source at Argonne National Lab, which is a really large synchrotron, beamline 2BM. This is what our custom cell looks like. It's a very, very small cell, kind of tricky to work with, actually extremely tricky to work with. It's airtight. What we do is we make a little tiny battery stack inside. We have lithium metal electrodes on either side of a solid electrolyte pellet. The solid electrolyte we're using here is a different one than what I just showed you. This is what we call LSPS, lithium tin phosphorus sulfide. It has high conductivity, but as we'll see in a second, it's unstable. It's chemically unstable in contact with lithium. So we take this cell to the synchrotron, and because it's narrow, it's a thin cell, it's only about 1 millimeter wide here where the stack of materials is. And because we've optimized it in various ways, we can actually take this cell, put it into the beamline, and then do X-ray tomography on the cell while we're operating it. And that's shown over here. So this is the electrochemical data where we apply current in one direction, then we reverse the current in the opposite direction to cause deposition and then stripping. And these purple vertical lines are interspersed tomography scans. So a tomography scan means that we take about 1,500 2D projection images as we rotate the cell. And each of these two-dimensional projection images is then combined into a reconstructed 3D image. So we get a 3D reconstructed image of our battery stack every 15 minutes throughout our entire experiment. So very useful, produce a lot of data, but we can track materials changes in the cell the entire time we're doing the experiment. And I should mention that the voxel size here, the resolution basically is about 1.5 microns. So here's what some of the data look like. So this is not a complete 3D scan now. This is only a single 2D slice through the cross-section of our cell. It's more than one slice because this is a video. I hope you can see the video. So it's a time series of slices, but a single slice across time. And what you see here is now we're looking at the stacked materials in the cell. We have the darker regions up here and down below, which are the lithium metal electrodes. In the middle, the thick region that has kind of a granulated contrast, this is our solid electrolyte material. And then at the top and the bottom, you can see this very white region. These are the steel pistons that are the current collectors. And what we're seeing here is basically the reaction processes in this cell over about the 10-hour experiment. And what you see is the lithium metal electrode shrinking at the top and then at the bottom as we're stripping lithium. You also see this intermediate contrast region growing at the bottom and then the top. This is the interphase. So I mentioned this earlier. What we're doing here is we're directly electrochemically growing the interphase, which is the reaction product of the solid electrolyte with lithium. We're doing this instead of depositing lithium metal in this system. We're growing interphase. So here you can see it growing at the bottom. Here you can see it growing at the top when we switch the current. So upon reduction, we grow interphase in this system. But we did a lot of work on this to segment out these various volumes, and we found that actually the lithium is being stripped very effectively during stripping, but during what we would refer to as deposition normally, we're not actually depositing lithium, we're just growing interphase. So I think that this video is kind of useful to look at to understand the dynamics of the basic dynamics of what's happening in our system. But what was really interesting is we were able to analyze this data in more detail. And we found that, in fact, after stripping the lithium, we often saw the presence of voids at the interface. So this is just another set of two images, the same location in our battery cell now. This is before stripping the lithium, and this is after stripping lithium. You can see before, even though we have a rough interface, there's fairly good contact at the interface. There's not significant contrast changes that would indicate voids. But after stripping, the same location, you can see that you have these dark spots at the interface, and these are voids, lack of material. And just as an illustration below, what we were able to do is we created these algorithms to go through all of our three-dimensional data and segment out the different phases, including the void phase, which has a very low intensity. So you can see the normalized intensity at the void spot. It's our lowest intensity. And so we're able to segment and separate the lithium intensity from the void intensity, from the solid electrolyte intensity. And that allows us to map across three-dimensional space the presence of all these different phases as a function of time. And the result is a lot of data, as you can imagine. Some of that data is shown here. So this is an illustration of a three-dimensional section of the interface, where we're looking kind of at an angle down through the lithium metal. So there's lithium metal on top of this, but we're not visualizing it in this visualization. The solid electrolyte is below, and there's interphase that's also grown below, which we segment out. But what we are showing on top of the solid electrolyte are these purple spots, actually purple voxels. And these purple voxels are the voids. So at the beginning of the experiment, we do have quite a few voids actually, because our interfaces were imperfect. But as we strip the lithium, you can see stripping quite a bit of lithium, not much really changes. But then at the end of the experiment, we stripped 4.5 milliamp hours per centimeter squared. And you can see that there's just a ton of voids that have grown in at the interface. We've lost contact substantially across the interface. So this is one way of looking at it, nice 3D reconstructions. That's pretty. I think this is potentially a more useful way. So here we're mapping out in this plot, we're mapping out the voltage curves of the cells. So here's stripping at the top interface and then stripping at the bottom interface. And we're also plotting the overall contact area at the bottom interface and also at the top interface in green. So there's two interfaces. We have two sets of contact areas. And so we're mapping this out with time at both interfaces. And what you see, what this data shows, is that the top interface doesn't really change very much. The contact basically remains quite similar. The bottom interface, there's some contact loss when we're stripping on the other side. But then when we start stripping at the bottom interface, towards the end of the experiment, we have a rather dramatic loss in contact and an overall reduction in the contact area. And this happens to correspond with the voltage of the cell polarizing strongly, negative over potential. And so this is one way of looking at it. This set of images below now shows what we call contact area maps. So now we're basically looking through the interface and we're projecting all the pixels of contact. So the yellow pixels are pixels where there is contact between the solid electrolyte and the lithium. And at the beginning, it looks like this. This corresponds to a high overall area of contact shown up in the plot above. And then as we cycle, we lose some contact area, but really in the last 45 minutes of the experiment, we lose half of our contact area. And not only these images below show that it's not only the overall magnitude of area that's changing, it's also the size of the contacting spots. We go from regions of relatively large contact area here to isolated contacting points here. And this turns out to be very important. Here is just a video of what the contact loss looks like over time at this bottom interface. That's kind of cool. But anyway, this turns out to be very important. We quantified the change in contact size with time. And we found that at the end of the experiment, 100% of the contacting points at this particular interface had this relatively small size, less than 0.02 millimeters squared. And we worked with actually Professor Mukherjee's group here at Purdue. They did some modeling of our cells and the materials and geometry of our cells to try to see if we could recreate the electrochemical curves we measured with the overall contact area loss that we measured. And so what we found is we can't, because we weren't taking into account these isolated contacting points. And so we have a much steeper increase in overpotential than we would expect based on just the overall area of contact. And so the moral of the story here is that it's the formation of these isolated contacting points, which is really important and which really drives the failure of our cell. This increase in overpotential corresponds to failure. And this is happening because when you're forcing currents to go through these very small contacting points, you exhibit this larger constriction resistance. It's constricted current, and there's a much larger resistance around the edges. And so this is what drives this increasing polarization of the cell. And so the overall contact positions and contact distribution is really important to understand in these cells to be able to predict the electrochemical behavior. So that's the outcome of these experiments. All right. Yes. Is that a question? Oh, I don't think so. I think somebody may just be off mute. Well, that's okay. Maybe somebody can figure out how to mute that microphone. Thank you very much. All right, so that's a good timing actually, because we're moving on to the second portion of the talk. So I want to talk a little bit about interphase growth. And so I mentioned this already in the previous set of experiments. I showed you with our X-ray tomography that we could image the growth of the interphase. It has a different contrast in the X-ray images. But I want to make some comments on interphase growth in general. So this is a problem with many solid electrolyte materials. This is a plot from a modeling study by Yifei Mo's group at Maryland, where they predict the electrochemical stability of a variety of different solid state electrolyte materials. These are the green bars here. And you can see that the overall voltage stability on the left here is quite limited for most of them. LLZO is the only material that has a voltage stability that approaches the potential of lithium metal, but it doesn't even get there thermodynamically. So basically what this means is that your solid electrolyte is not going to be thermodynamically stable in contact with lithium or cathode materials in many cases. And so you expect to have some sort of structural evolution at the interface, which can be quite complex. So this is from some previous experiments where we were investigating a different solid electrolyte material. This is an oxide material, LAGP, lithium, aluminum, germanium, phosphate. It's a Nasicon type ion conductor. It has slightly lower conductivity than the sulfides I was just showing, but it was quite useful for these experiments. And in these experiments, we were investigating what happens at the interface when you contact lithium metal to this solid electrolyte material. So thermodynamically, based on calculations like this, you expect a bunch of binary phases to form. So you expect with this material, you might expect lithium aluminum and lithium germanium phases to form, as well as the phosphide and oxide phases. And so, you know, when we started this work a few years ago, we didn't really know if these binary phases would form or not. Thermodynamically, they're expected, but there's also kinetics aspects that are important. And so we decided to investigate these details with a variety of different experiments. So one of the things that we did was in situ TEM. And I won't dwell on this right now because I'm going to show a little bit more data in about 10 minutes on this. But these are some experiments we do in my group where we basically bring a material of interest in contact with lithium. And so we do that here with this solid electrolyte material. So here's a little crystal of a solid electrolyte, this LAGP material. And we're bringing it in contact with lithium inside a TEM at fairly high magnification. And you can see here that there's an expansion process, there's a reaction process. And what we're doing here is we're amorphizing the initially crystalline solid electrolyte to form an amorphous phase. So this is a big structural change when we react with lithium. So the interphase process involves reduction, and in this particular material, it involves amorphization. So this already gives you a hint that we're probably not forming these thermodynamically stable compounds. To investigate the impacts of interphase formation, we carried out some more X-ray tomography experiments. These were slightly different. They were carried out in a lab scale tomography instrument rather than a synchrotron. But the idea is the same. The resolution is a lot worse, but the idea is the same. But in this particular material, we basically, we took lithium metal, we sandwiched this LAGP pellet with lithium metal, we cycled it back and forth kind of like we did before, as I showed you. And these are now X-ray image slices from the middle of this LAGP pellet as we cycled this battery over 52 hours. So it's a longer experiment. And I think the most distinct thing that you can see here is that there's these dark lines that grow in as we cycle this. And in fact, these lines are cracks. And so we are cracking and fracturing this solid electrolyte pellet into a bunch of pieces, actually. And you can see in this bottom set of images, this is the 3D fracture pattern that we've segmented out from this data. So it's almost a spider web-like pattern of cracks. And so this is different than the data I just showed you. In the synchrotron data with the sulfide solid electrolyte, I showed you that we lost contact at the interface, and that caused failure of the cell. Here, the cell is a little bit different. This is done in a coin cell, and there's contact loss is less of a problem. But we're seeing here all these cracks are growing in, and that's different than what I showed you before. So this is a video of the fracturing process of one of these image slices. That's kind of interesting. The most important thing we learn from these measurements beyond these videos is that it's the fracture process itself which is driving the increase in impedance in these cells. And that's shown with this data here. So you can see that the impedance in the blue points here corresponds to the y-axis. This is increasing dramatically only when we start damaging the material through fracture, which is shown in these red triangles. So that makes sense. I mean, cracks cause impedance increase because they prevent ion motion. But there's a little subtle thing here that's interesting. What we found through these experiments is that, well, what we know is that interphase is growing on the top and bottom interfaces here the entire time during these experiments. So we have the formation of these new phases at the interface on the top and bottom. But during this process, actually, during interface growth, there's really very negligible impedance increases. It's not until we start getting fracture where our cell fails and our impedance increases substantially. So we learned that actually the interphase itself is not really causing electrochemical failure here. Instead, it's the fracture process. And this is a little bit different than what's been assumed in some other studies, which is why we were excited about this. So with that being said, we worked with Claudio De Leo's group at Georgia Tech to do some mechanical modeling of interphase formation. And it turns out that all these these cracks in the fracture process here is basically caused by interphase formation. So you have the growth of this we're looking here at a half of the cross section of one of these pellets. This is a finite element model. And the interphase is this black region up here. It's this expanded region. It's an amorphization expansion process. There's lots of volume change. And so this volume change induces tension in the rest of the pellet. And this tension pulls the pellet apart. And this particular pattern is consistent with what we expect the stresses to be in the pellet. So this is a little bit different than maybe others in the audience may know of filament-induced fracture due to short circuiting in filaments. So this is different than that because we have such an unstable solid electrolyte, but pretty interesting. In the long run, interphase formation is bad after all, but we're able to quantify how it affects failure here. Okay, great. So I'm on to my last section here. I think it'll take another 15 minutes or so. I think that's good. That's within the realm of our time here. I don't want to hold you for too long. But I'm kind of going to switch gears a little bit and talk about some of our more recent work on investigating alloy anodes within solid state batteries. And we're quite excited about this for a number of reasons. So I'll give a little bit of background here on alloy anodes if you're not familiar with them. So alloy anodes, so far I've talked about lithium metal as an anode. You know, lithium metal is probably the ideal anode. It has a very high lithium ion capacity. It's very light. You can basically store more lithium in lithium metal than you can in anything else. But there are other options, and they have particular reasons why you might want to use them. One option is these alloy anodes. So alloy materials are, as it sounds like, materials that alloy with lithium atoms. Examples are silicon and tin and antimony. They're actually quite interesting because not only do they alloy with lithium, they alloy with a lot of lithium. So for instance, silicon will expand in volume by about 300% during incorporation of four lithium atoms per silicon atom. So this corresponds to very high theoretical specific capacities. And in many cases, they could give you overall energy density performance that's quite similar to lithium metal, depending on your battery geometry. So these have been studied for decades. We've known about them for a long time, and they're currently being commercialized for conventional lithium-ion batteries with liquid electrolytes. It's been very challenging, though, because these big volume changes during charge and discharge, the volume changes of the particles inside the battery, what they do is they cause mechanical fracture and they cause continued growth and contraction of the surfaces, which exacerbates side reactions in liquid electrolytes in particular. Going back to the very beginning of this talk, because liquids can wet surfaces regardless of how they change, you grow what's called the solid electrolyte interphase on the surface of these alloy anode materials. And every time you expand and contract your alloy anode, you form new surface films. So this basically eats up your electrolyte and reduces the efficiency of your cell. So right now in the commercial landscape, there are companies, including Sila Nanotechnologies, who are commercializing these materials at large scales, which is very exciting, but they're primarily really only, as far as I know, for lithium ion type cells, liquid electrolytes. So we're interested in seeing how these things behave in solid state batteries, because if we can, there could be some advantages. In solid state batteries, you don't have a liquid, for instance. And if we can get them to work in all solid environments, we may be able to cycle with these alloy anodes more efficiently. than liquids. But there's this problem of large volume changes still, and we want to understand how this affects the chemomechanics in an all solid environment. This is what we set out to do. Before I get into the solid state data though, I do want to mention, kind of as an aside, that my group does quite a bit of work, or has done quite a bit of work, on understanding alloying mechanisms at very small length scales in these alloy type anode materials. So this is from a paper down here I've cited, where we investigate the reaction processes of very small antimony nanocrystals. Antimony is a metal that reacts with lithium and alloys with lithium. And so we use this same in situ TEM setup so we can probe reaction processes at very small length scales. And it's pretty interesting. What we find is when we lithiate these particles, by the way, I run through this part kind of quickly, so I apologize. There's a lot of details associated with how we do these experiments. If you're interested, we can talk after the presentation perhaps. But for now, I guess you'll just have to trust me that we do them well. I hope you will. But anyway, we have these little crystals and we're able to lithiate them inside the TEM, which is pretty cool. And when we do this, we see this process here. There's an expansion process. These are now lithiated nanocrystals. But very interestingly, we found in this particular study that when we delithiate these crystals, there's this formation of these hollow structures. And this is what's happening here is we have this outer oxide shell, which is constraining the contraction of these materials. And so it prevents them from shrinking. And instead, it causes the pure antimony to kind of go to the surface, as you can see in the schematic down here. So I show this just to illustrate that we do experiments to probe fundamental reaction mechanisms in alloy materials. And in fact, we found some pretty interesting mechanisms. And the reason why this sort of thing happens is because we have these very large volume changes. That is atypical of general materials transformations. So I want to just show the video here of this delithiation process. These are these lithiated nanocrystals undergoing lithium extraction. So lithium is leaving. You can't see the lithium leaving. What you see is the antimony shrinking and forming these hollow structures surrounded by the oxide shells. And so this paper, we're pretty proud of this paper. If you're interested, you can check this out. We developed this model in this paper that shows that this is a size-dependent process. We see that experimentally too. But there's opportunity for controlling structural and volumetric changes through the use of these coatings, as we've seen from this paper. So this is my 2 slides on the in situ TEM study and the work that we've done in this area. Overall, we've looked at alloying mechanisms. This is very important for understanding when we think about adding these sorts of materials to solid state batteries. Which brings me to our studies on using alloys in solid state batteries. So in these studies, we're testing now scaled, or maybe not scaled, but we're testing full solid state battery cells. This is an important detail to mention. So we make these cells as shown here. They're in a compression type cell setup. We're using this solid electrolyte here. This is the argyrodite. Now we're back to it. We talked about it in the very beginning. Lots of different solid electrolytes today. I apologize if that's confusing. But in these cells, we have an alloy-based anode. It's a composite where we mix, in this case, silicon particles with the solid electrolyte material, and we compress it to form kind of a pellet structure. And then on the other side of the battery, we have an NMC 111 cathode. And it's the same situation where we're mixing the active NMC material with the solid electrolyte. And so what I want to show you is first the performance of these types of batteries. So we use these silicon microparticles. These are just commercial Sigma Aldrich silicon microparticles, 5 to 10 microns in size. And so this is the anode. And we cycle this as shown here. And the results, the capacity retention is shown below. So the aerial capacity is a little low in this particular configuration, but what we're seeing is very good capacity retention over 100 cycles here. And this is with just standard non-treated, non-nanostructured silicon microparticles as the anode. So I think this is the really exciting part. We're showing that there is some promise here of using these microparticles. This is published here in this Joule paper from earlier this year. So if we compare this to what these similar particles, how they behave in a liquid electrolyte battery that's shown here, they rapidly decay, basically. And this is because of this volume changes and the SCI formation and all that I talked about already. So long story short, we've seen we have evidence for really promising behavior of these alloys in solid state batteries. And it's driven by the fact that you no longer have the liquid, at least we think it's driven by the fact that you no longer have the liquid to form these extensive SEI films. I should quickly mention here, earlier this week or last week, Shirley Mung's group also published a very nice paper in Science on silicon-based anodes for solid-state batteries. Highly recommend checking that out. Very exciting. So, there's multiple groups out there now that have shown, theirs is particularly impressive, more impressive than our data here. But I think it illustrates the overall promise. Okay, so here, this is a promising system. So what I want to tell you about now is some of the more detailed chemomechanical investigations we've done to understand specifically how stack pressure is related to the transformations in these sorts of batteries with alloy electrodes. So stack pressure isn't something that I've talked about in detail yet. It turns out to be extremely important for solid state batteries. A number of these papers cited down here have done some really nice work on both understanding the effects of stack pressure on lithium and also understanding how stack pressure changes when you cycle. So we were inspired by this work down here to carry out some investigations of monitoring stack pressure, with applying it and then monitoring how it changes due to the reaction processes in our electrode materials. And again, this is published in our Joule paper down here. So to do this, we built these custom cells here. There's a constant volume cell casing in these cells. You can see these look more like a uniaxial press than a solid state battery. But what this does is allows us to apply a controlled stack pressure with a torque wrench on these bolts up here. And then this is our very small battery stack down here, about 1 centimeter in diameter. And we also have a force sensor integrated into this stack, so we can measure the stack pressure that we're applying. And very importantly, we can also measure the stack pressure and how it changes when we cycle the battery. Turns out this is very important. This is a cool set of images over here. This is a fib cross-sectional tomogram, basically, of one of these alloy composite electrodes. So again, this is the negative electrode in our battery down here. In this particular case, we're using antimony as our active material. I will show you data from 3 different alloys: silicon as the active material, antimony as the active material, and tin as the active material. All we found worked pretty well. Silicon, we investigated the most. But in this data set here, you can see this is the composite structure. The lighter regions are the antimony particles. They're rather large. The darker regions are the mixed in solid electrolyte, which is the argyrodite material. It's a little smaller. And then we also have these black regions, which are pores and voids. So this is really not an optimized structure, actually. We would like to get rid of some of those voids probably. But anyway, we use this and the intention here is to understand how, with these interesting electrodes that can show high performance, how does stack pressure change with cycling, and how does that relate to the materials transformations? And so here is a pretty extensive data set. What each one of these plots shows on the top and the middle and the bottom here is now the charge and discharge of a solid state cell. On the top, it's an antimony electrode at the anode. In the middle, it's a tin electrode. At the bottom, it's silicon. And so this is the voltage curves in black for each case. They all look different because you have different plateaus and everything. And then in red, you can see this is the stack pressure change, or the stress change. So each of these cells starts at 20 megapascals applied stack pressure. And then when we charge, you can see that the stack pressure increases. And then when we discharge, it decreases, and then it's cyclic from there. Increase, decrease, increase, decrease, increase, decrease, etc. And so that's the same for all these materials, but some of the details are quite different. And so it turns out by investigating the details of how the stack pressure changes, we can learn some things about these composite electrodes. One of the big conclusions, though, is that there are much larger stress changes in these cell stacks than what you find in liquid cell batteries. Similar measurements have been done in conventional liquid cell batteries with alloys and with lithium. And you see, depending on the cell configuration, which is important for this, you see, hundreds of kilopascal changes, whereas here we're seeing multi-megapascal changes. This is also important because it's thought that for a commercial solid-state battery, you really do need low stack pressure on the order of 1 megapascal or less. So here we're showing that the change of stack pressure, and I'm going to show you that this is due to just the transformations of the materials inside, fundamental intrinsic transformations, this change in stack pressure is on the order of what you need the applied stack pressure to be. So this is interesting because it's either a problem, because this would be a significant change in stack pressure in reference to the baseline, or is a potential opportunity, because what we're showing here is that the materials themselves can effectively apply a stack pressure in a constrained environment that's on the order of what you need to enable good cycle life. So I think that's an interesting piece of food for thought. All right, so why is this happening? This is very well described by our understanding of partial molar volume of lithium when you compare the cathode to the anode material. And the basic idea is that the partial molar volume of lithium in these alloys is larger than it is in the cathode materials. And so this has been quantified by a great paper by Jürgen Janik's group, Raymond River, from a few years ago, plotting the partial molar volumes of lithium in these various materials. And the basic idea is that in the discharge state, you have your cathode and your anode like this. In your charge state, your cathode decreases in volume a little bit, but your anode increases in volume a lot. So this is like kind of the non-quantifiable way to say this. The partial molar volume of lithium is larger in the anode than the cathode. And so you have an overall volume increase of your stack. And in this constrained cell environment, this results in an increase in pressure. And that's what we measure. And this is why this is happening. And so a little bit more detail now. What we can learn from this with these composite electrodes, you find some interesting things. So first of all, if you compare this composite tin electrode to a planar electrode, so a tin foil that's just a flat interface, two different cells, you see that in the composite structure, you have a large hysteresis in the stress. So we're charging and the stress is increasing here, and then we're discharging, the stress is decreasing, but it does not occur on the same pathway, and there's a hysteresis. And with the planar foil, you don't see this hysteresis, or at least in some cycles, it's a lot smaller. And we think this is because the composite structure has extra void space and other features that can accommodate some of the volume expansion of the particles, which causes this stress hysteresis. So basically, the evolution of stack pressure is affected by the structure of the electrode. Very important. We also found that the size of the active material particles in the composite affects the overall stress change quite a bit. So we did a direct comparison between silicon microparticles and silicon nanoparticles, and there's a lower overall stack pressure change when you use the smaller particles. And this, again, is because we think the expansion of the smaller particles can be effectively accommodated by excess void space more easily than the larger microparticles. And so this is some of that data here. So basically, these experiments helped us to understand some of the details of how the electrode structure can affect stack pressure evolution. And finally, I'll just say there's this paper we're also quite excited about that came out about a month ago, where we use similar stack pressure measurements, but instead of investigating alloys, we investigate lithium interfacial behavior. So we examined the differences between interphase formation in an unstable system and filament formation in a stable system. And we're able to detect differences in the signatures of stack pressure due to interphase formation and lithium filament growth. So check this out if you're interested. The citation is down here. All right, so I'm coming to the end here. I'll just quickly say to conclude this section that I kind of mentioned some of this already. We see these relatively large changes in stack pressure during charge and discharge of alloy anode-based batteries, much larger than liquid cells. And there are important implications for particle connectivity and interactions within an electrode structure. And I think that this sort of stack pressure measurement can be quite useful for understanding some of these details. All right, with the last few minutes here, I'm going to have a few thoughts. I was asked by the ECS committee here to comment a little bit on career pathways. And I know there are a lot of students on the line probably, so I'll just spend a minute or two talking about this. The first thing I wanted to say, first thing that came to mind when I was asked about this, was that there is really just an enormous growth in demand for people, students and newly graduated students that have some sort of knowledge of electrochemistry and energy storage systems. And probably a lot of you know this already because the energy storage industry is growing dramatically in the US and around the world. But what I'll say is there's really never been a better time to learn about electrochemistry fundamentals, do electrochemistry related research and get into the battery industry if that's what you want to do. And I'll say you don't have to get a PhD. You know, you can get a master's, you can get a bachelor's. A lot of these smaller and larger battery companies are hiring all sorts of engineers in many disciplines, not just with electrochemical knowledge, but with manufacturing knowledge, materials knowledge, chemical engineering knowledge to build this new battery industry. So it's really very exciting. This was not a thing 10 years ago. So we're moving into a very exciting frontier. A few more thoughts on a research-based career. So for the PhD students in the audience or postdocs, I think this might be useful. Well, I said starting research early as an undergrad is great. Of course, if you're already a PhD student, that's a little bit late piece of advice, but probably many of you did undergraduate research. I think this is one of the most important things that is available for undergrads these days, to be able to do high quality undergrad research. For PhD students, I would say seeking out mentors beyond your advisor is very useful. I had a few mentors in grad school that have been really supportive as my career has gone along. So don't be hesitant to reach out to faculty that you're interested in having conversations with. They'll be excited to talk to you, hopefully, especially if there's some crossover of disciplines and ideas. For PhD students that are looking to do a postdoc, I think it's quite valuable to potentially get into a new area as a postdoc, maybe related in some ways, but also expanding your research horizons. And the last thing I'll say is, even though you have to work with your lab mates now or your group mates if you're doing computational research, and maybe of course they're your friends, but they're your coworkers as well. You should remember that they'll eventually be your peers in the wider world with jobs all over the place, and they'll be leaders, and you will too, probably. And so the connections you make today with your fellow grad students are very important for the rest of your career. So don't forget that either. All right, I hope this is useful. It's my thoughts on career pathways. So with that, I'll finish. My conclusions are that in basically all the examples you saw today, there were quite a few, so I hope it wasn't overwhelming. But in all these examples, the relationship between chemistry and mechanics was really important. And in fact, in solid state batteries, this is really a defining feature. And I also showed you a number of different in situ techniques and operando techniques. These are also really critical for understanding the inner workings of many energy storage systems, including solid state batteries. So with that, I'd really like to thank my group. They've done all this work. So the people on the solid state team that have contributed and have led these efforts are Jack Lewis, Francisco, who's graduated, Jared, who did some of the early work in this area, Song, who's now at Tesla, Emily, Klein, and Eugene and Lars are newer members of the solid state subgroup. Matthew Bobinger is now at Oak Ridge National Lab, and he did some of the in situ TEM work. So it's been a group effort. We have a relatively large solid state team. It's a very exciting area. I'll stop there. Happy to take any questions if we have a little bit of time. So thank you very much for your attention.